can also be useful in the study of Igusa zeta functions. Everything I'm going to explain is part of joint work, first with Mircea Mustața and then with Chen Yang Xu. And in fact, this is work that goes back already a couple of years now. And so I want to explain some of the relations that exist between Igusa zeta functions, weight functions, and on Berkovich spaces, string theory, and the minimal model program. So I'll start introducing well, some of the ideas and motivation behind Igusa zeta functions. And again, many of you will know this by heart by now, but it doesn't hurt, I guess, to repeat it. So we pick a non-zero polynomial f in n variables with integer coefficients. We pick a prime number p, a positive integer d. And then we can look at an elementary counting problem. We can count the number of solutions of the congruence f equal to 0 modulo p to the power d, where we consider solutions as elements of or tuples of residue classes modulo p to the power d. And so obviously, well, we only have finitely many coordinates to choose from. So the number of solutions is finite, and we denote this number by NFPD. Then a basic question one can ask is, what is the asymptotic behavior of these numbers when we let d tend to infinity? So when you're confronted with this type of problems in number theory, it's usually convenient to put these numbers into a generating series. So we define a power series, which I will denote by Q index Fp to keep track of the polynomial f and the prime number p. And so this is just a formal power series whose coefficients are these numbers of solutions of our congruence f equal to 0 modulo various powers of p. And then, well, we would like to detect the patterns that exist between the coefficients of this generating series. And well, one type of pattern that can occur is well, some kind of recursive pattern that causes this series to be rational. So that question was raised by Borovich and Shafarevich in '66. Is this a rational function? Is it a quotient of two polynomials with integer coefficients? So an immediate thing we can observe is that this question is actually quite easy when f has no singularities modulo p. So more precisely, if we look at the zero locus of f in affine n space over the integers, if this thing is smooth at every point lying above the prime p, then we can just use Hensel's lemma. And Hensel's lemma tells us, okay, we count solutions modulo p. So that's this coefficient here, NFP of 1. And then each of these solutions will lift to p to the power n minus 1 solutions modulo p squared. Each of those will lift again to p to the power n minus 1 solutions modulo p cubed, and so on. So our numbers, NFPD, they form a geometric series. And so the generating series is just given by this, this easy expression. But as soon as f has singularities, then the problem becomes much more tricky. The shape of this generating series can be quite complex. In this case, it was still proved that the generating series is always rational, and this was a major result by Igusa in 1975. So before recalling the strategy of Igusa's proof, let me show you well, an elementary example in the sense that we take a singularity that's as simple as can be. But as you see already, the shape of the generating series is complicated. So we just look at polynomial f in two variables given by y squared minus x cubed. So this defines the cusp singularity in the plane. And then, well, here you can still compute the series by hand if you're sufficiently brave and patient. And so it's convenient to slightly rescale the variable by replacing t by p to the power minus 2 of t. So the 2 in the exponent is the number of variables in this case. And then we can express the series as, well, a fraction of a pretty complicated numerator, which we won't say too much about here. And then a denominator, which contains two factors. So 1 minus p to the power minus 1 of t times t. This is the factor that would also appear in the smooth case up to this rescaling operation that we have performed. So this is somehow the factor which is there when there are no singularities at all. And then here we have an additional factor, which is somehow related to the singularity of the cusp at the origin. And so the exponents that appear in this factor 5 and 6, these you should keep in mind because they will appear again in a moment in a, well, seemingly different context. So how did Igusa prove rationality of this generating series? Well, the key insight is that we can rewrite the generating series as a p-adic integral. We consider a complex variable s with real part positive, and we perform a substitution t equal to p to the power minus s. Then modulo a simple transformation, our generating series qfp of t can be written as a p-adic integral. So we integrate over zp to the power n. The function we integrate is a p-adic absolute value of f raised to our complex power s. And we integrate with respect to the Haar measure dx on zpn. And so, well, if you haven't seen these p-adic integrals before, that's okay. It's not terribly important how they are defined, but what is important is that they satisfy similar properties as integrals, and crucially, they satisfy a form of change of variables. And so Igusa's idea was to perform a convenient change of variables so that we can explicitly compute the integral, at least locally on the domain after this change of variables. And so the change of variables that we use here is a resolution of singularities.
Well, these are not really integrals, right? They're just finite sums.
No, these are infinite sums.
Infinite sums still.
Yeah.
But the functions are locally constant.
They are locally constant, but you get an accumulation of values when you approach the zero locus of f.
Mm.
That's right. If you remove the zero locus of f, then the domain is no longer compact, and so you an actual infinite sum. So, well, resolution of singularities here can be viewed as some kind of surgery that we perform on the domain of integration to make the polynomial f monomial in local coordinates. And geometrically, it means that after this surgery, the zero locus of f becomes a divisor with strict normal crossings. So we can look at an explicit resolution again. I mean, for all of you, this will be quite familiar, but just to keep a picture in mind. So we start from the cusp singularity that we used before. So this is one singularity at the brown dot. And then we resolve the singularities by blowing up. So after blowing up 3 points, we see that the total transform of the blue curve of the blue cusp is indeed a strict normal crossings divisor. And so we have, well, the blue component, which is a strict transform of the cusp, and then 3 exceptional components, the exceptional divisors of the 3 point blowups. And so, well, once we've performed this resolution of singularities and the corresponding change of variables on the integral, then the expression that we are integrating becomes monomial in local coordinates. So locally, we can compute this integral explicitly. And what you get is that you get a finite sum of rational functions in p to the power minus s. So this means that z are, well, this is Igusa's p-adic zeta function, is rational in p to the power minus s. And our generating series is therefore rational in t, because it's related to the zeta function by a simple transformation. So, well, since our integral is rational as a function of p to the power minus s, it has a meromorphic continuation to the complex plane. And so this meromorphic continuation is still called Igusa's p-adic zeta function. And by the relation between the zeta function and the generating series, we can say something about the asymptotic behavior of our coefficients of the generating series, our numbers of solutions of congruences, modulo powers of p, by studying the poles of Igusa's p-adic zeta function. So now the problem has become a bit different, a bit more geometric. a bit more analytic, we try to understand the poles of this p-adic zeta function that we have defined. And so in fact, if we investigate Igusa's proof, we get some information about the shape of these poles. Because if we perform resolution of singularities to reduce the zero locus of F to a strict normal crossings divisor, we can attach numerical data to each of the irreducible components in this divisor. So first of all, we can attach a multiplicity to this divisor, and this is just the order of vanishing of F along this component. And we can consider the log discrepancy, nu. So this is an invariant that measures the complexity of the resolution. So nu minus 1 is the order of the multiplicity of the component in the relative canonical divisor of the. And on the picture, I've computed these numerical data in the example of the cusp singularity. So we have, our blue curve. This is just a strict transform of the original cusp. So since it's a strict transform, our log discrepancy is equal to 1. This component does not appear in the relative canonical divisor. And then for the other components, the log discrepancy goes up in every step of the blow up. So for the brown component, it's 2. For the green component, it's 3. And then for the yellow component, it's 5. Because, you somehow remember that you've blown up a point which is already contained in the exceptional locus. And then for the multiplicities of F along these components, we get 1 for the blue guy. So that's just a strict transform. 2 for the brown guy, 3 for the green guy, and then 6 for the yellow guy. So that's just an easy calculation that we can make in local coordinates on the blow up. And so these numbers 6 and 5, they should be familiar because these were exactly the exponents that showed up in our denominator of the rational expression for the generating series of the cusp singularity. And so the point is that this is not a coincidence. Igusa's calculation shows that if S0 is a pole of the p-adic zeta function, then its real part is of the form minus nu divided by n for some pair of numerical data n nu that are attached to the resolution. And moreover, the calculation also shows that the order of each pole is at most n, the number of variables in the polynomial. And so this theorem tells us that for each pole, there should be a component in the resolution such that minus nu over n is the real part of the pole. It doesn't tell you the converse implication. And in fact, it's still a very difficult problem to determine which of these numbers minus nu over n are actually real parts of poles. So that's essentially the content of Igusa's monodromy conjecture, which puts an additional restriction on the numbers that can be actual poles or real parts of poles of the zeta function. For one thing, the p-adic zeta function is independent of the choice of a resolution, whereas the numbers minus nu over n, they will depend on the resolution in general. But even if you only take the fractions minus nu over n that occur in every possible resolution, you still will have a set which is much bigger than just the real parts of the poles of the zeta function. So there is something going on there. We need an additional criterion to shift out or to sift out the actual real parts of poles from this set of candidates.
Good question. So there are poles with non-zero imaginary parts.
I'm sorry?
Is there poles with non-zero imaginary parts?
Yes. Our p-adic integral is a function of p to the power minus s. So it will be periodic in 2pi over logarithm of p.
And is there any interpretation of this imaginary parts somehow?
Somehow the imaginary parts, they start playing a more visible role if you look at zeta functions which are twisted by characters. But I don't know if there's a solid conjecture that kind of predicts what they should be. But Wim can correct me if I'm wrong.
No, this is not really investigated, and I'm not sure, yeah, whether people expect something.
Mm-hmm.
So the conjecture that I want to talk about today is not Igusa's conjecture, but actually one of Wim's conjectures. So this has to do with an invariant called the log-canonical threshold. So this is the minimum of all these fractions nu over n, computed over all the components in the total transform of the zero locus of f on the resolution of singularities. So this log-canonical threshold is abbreviated by LCT. So one striking property is that this is actually independent of the choice of resolution. So even though the set of all fractions nu over n depends heavily on the resolution, the minimum of this set does not. So it's a well-studied invariant because it's actually one of the most important invariants in birational geometry. So this is the key invariant that is used to classify singularities of pairs. So if you try to put pairs consisting of a variety and a divisor in classes according to the nature of the singularity, in the minimal model program, this distinction is made based on the log-canonical thresholds. And then from the point of view of our accounting problem, this is somehow the dominant contribution to the asymptotics of the numbers of solutions of congruences modulo p to the power d as d goes to infinity. So you can show that for maybe excluding finitely many prime numbers p if necessary. The largest real part of a pole will be minus the log-canonical threshold, the pole of the zeta function. And so in this sense, the log-canonical threshold will control the asymptotic behavior of the coefficients of our generating series. So I've mentioned before that Igusa's calculation shows that the largest possible order of a pole of the p-adic zeta function is n, the number of variables. And so Wim conjectured in 1999 that if you have a pole of order n, then the real part of this pole is also as large as possible, and namely it must be minus a log-canonical threshold. So that's the result I proved together with Chen Yang, and well, the result was published already a couple of years ago, as I said. So I want to explain a couple of ingredients of the proof. So first, I will try to explain the motivation behind the proof. And then in the second part of the talk, I will explain the actual proof. So somehow the motivation seems very different from the actual proof itself. The actual proof is based on technical aspects of the minimal model program, whereas the motivation behind the proof comes from non-archimedean geometry and mirror symmetry. So what I want to explain is how these two are related to each other. And so in order to explain why such a result could be true, we use a new way to package the numerical data into a picture. So we try to visualize the numerical data and the combinatorial properties of the resolution of singularities by defining a weight function on a dual intersection complex. So this is quite similar to what you've been studying in the past couple of weeks, where dual intersection complexes appeared as Skelata-Berkovich spaces, and where you looked at discrepancy functions or other types of weight functions on these spaces. So in this case, a dual intersection complex is a finite simplicial complex sigma that encodes the combinatorial structure of the zero locus of f after resolution of singularities. So we pull back the divisor of f to a strict normal crossings divisor on the resolution. And then we build this dual intersection complex to encode how the different components in the resolution intersect each other. So by definition, the vertices, they just correspond to the irreducible components of the strict normal crossings divisor. The edges correspond to connected components of intersections of two irreducible components. So more precisely, if we have two irreducible components corresponding to two vertices in the dual intersection complex, then the number of edges between these two vertices equals the number of connected components of the intersection of the two irreducible components. And so this goes on in higher dimensions. Well, the maximal dimension of a simplex is n-1. And the n-1 simplices, they correspond to connected components of intersections of n irreducible components. We don't have anything in higher dimension because by definition of a strict normal crossings divisor, the number of components intersecting in a point can never be larger than the number of variables, the dimension of the ambient space. So the maximal dimension of sigma is n-1. And well, I've included a couple of simple pictures to illustrate this concept. So on the left, you see the total transform of the divisor of F on the resolution of our cusp singularity that we've used before. And so on the right, you see the dual intersection complex. So in this case, in the two variable case, the dual intersection complex is also called a dual graph because it's 0 or 1 dimensional. And so it has 4 vertices corresponding to the 4 irreducible components in the divisor of F on the resolution. Well, these vertices are color-coded to correspond to a specific divisor. And then 2 of these vertices are attached by or are connected by an edge if the corresponding components intersect. And so the intersection of 2 components here is never disconnected. So we can never have more than 1 edge between 2 vertices. And we have an actual edge between 2 vertices even only if the corresponding components intersect. So this gives you the picture on the right, which is the dual intersection complex in this case. Then, well, for some examples in higher dimension. So the simplest example, or generally new example in dimension 3, is the case where we look at 3 coordinate planes in 3 space. So we have 3 irreducible components, each of the coordinate planes. So we have 3 vertices, which are again color coded according to the component that they represent. Then every pair of irreducible components intersects in a coordinate axis. So we get 1 edge between each pair of vertices. And then finally, the 3 components intersect in 1 point in the origin of 3 space. So we have 1 2-simplex, which is spanned by the 3 vertices. And so the dual intersection complex in this case is just a standard 2-simplex. Then, well, to get something which is topologically a little bit more interesting, we can extend the divisor on the left by adding a new plane, which somehow slices the first orthant diagonally. So this means that, well, to our previous picture, which is now the triangle on the bottom, we need to add 1 new vertex corresponding to the new red components. And then this vertex is connected by an edge to each of the previous vertices, because still every pair of components will intersect in a point. And then we also get 3 new 2-simplices corresponding to the 3 triple intersection points. And, so what we get this time as dual intersection complex is the surface of a tetrahedron, which is no longer contractible. Now it's homeomorphic to S2. And so this kind of more interesting topological object can also occur in this context. So this object tells us something about the combinatorial properties of the total transform of F, but we also need a gadget that keeps track of the numerical data. And so this is achieved by defining a weight function. So here we can define the weight function to be the unique function from our dual intersection complex sigma to the reals, with the property that it is affine on every face and assigns the value nu over n to each vertex. And so by definition, the vertices of sigma corresponds to the components in the resolution. Each component comes with numerical data n and nu. And so the value of the weight function at the vertex is defined to be nu over n for this pair of numerical data. And so one thing we can immediately see is that the minimal value of the weight function is precisely the low-canonical threshold. Because since it's affine on every face, the minimal value will be achieved at a vertex. And so we just need to take the minimum of the values at all the vertices, so the minimum of all the nu over n's, which is by definition the low-canonical threshold. And now we propose the following slogan. The idea is that we should think of the weight function as inducing a gradient flow on the dual intersection complex in the direction of decreasing weight, so that this flow collapses sigma onto the locus of minimal weight. So that this flow induces a strong deformation retraction of the entire simplicial complex sigma onto the locus where this weight is minimal. So I will explain in a little bit where this idea comes from, why we were led to propose such a slogan in the first place. But now let's see what we can do if we actually take this seriously.
So is this slogan literally true, or is this sort of just an idea?
At this point, it's just an idea. So I will explain in what sense it's literally true. And actually, there should be an even finer sense in which it's true, but that's very much under construction.
Okay.
There should be a more precise theory of gradient flows on simplicial complexes that allows you to write such a thing with mathematical rigor. But at this point, for us, it's just some kind of mantra that we use to discover actual theorems.
Okay.
So let me show you an example. We again take the weight function for the cusp. And so, well, we've already computed the dual intersection complex on one of the previous slides. So now I've just decorated each of the vertices on the right with the value of the weight function at that vertex. And so we had numerical data 1, 1, 2, 2, 3, 3. So the fraction is always equal to 1 in that case. So the weight function takes value 1 on the green, brown, and blue dot. And then for the yellow component, numerical data were 6, 5. So in this case, the weight function takes value 5 over 6 at the yellow vertex. And this is also the low-canonical threshold in this case, because that's the smallest value of the weight function. And so on the edges, connecting each of these 3 pairs of dots, the weight function is just an affine function with respect to a natural metric that we can put on each edge. So in this case, and more generally for any polynomial with 2 variables, you can turn the slogan into a theorem, because here it's clear what is meant by following the weight function in direction of decreasing weights. If we put ourselves at any point of the dual intersection complex of the graph sigma, well, there's always one direction where the weight will be decreasing. And if we keep following that direction, then we arrive at the locus of minimal weight, in this case, just a yellow dot, low-canonical threshold. So as I said, to answer Robin's question, how to translate this slogan into a precise mathematical statement is still not so clear. But one can extract a couple of precise theorems from this idea. And so the first theorem, which is the key to Wim's conjecture, is the following. Suppose that the weight function is constant on a maximal phase of sigma. And so maximal phase means a phase that's not strictly contained in a bigger phase. Well, in that case, the value of the weight function on this phase is equal to the low-canonical threshold. So why is this theorem some kind of, or why is this theorem implied by the slogan? Well, suppose that you place yourselves at an interior point of such a maximal phase of constant weight. So we expect that the weight function points us in a direction that we can follow in direction of decreasing weight until we arrive at the locus of minimal weight, so the locus where the weight is the low-canonical threshold. So if the weight function is constant on a maximal phase and we're at a point in the interior of this phase, then the weight function looks the same in every direction, and so we don't have any direction to follow at all. We don't see a gradient flow. And so according to the slogan, this is only allowed to occur if you're already in the locus of minimal weight. So if on this phase, the weight function is already equal to the log canonical threshold. So I will explain the proof of this theorem in the second part of the talk. So this is heavily based on a minimal model program. But so first I want to explain how this theorem implies Wien's conjecture. And then I want to explain where the slogan comes from. So suppose that we have a pole S0 of order n. And so we're trying to prove that the real part of this pole is minus the log canonical threshold. So if you again look at Igusa's proof of rationality, well, I already mentioned that this implies that the real part of a pole must be of the form minus nu over n for some pair of numerical data that appears in the resolution. But in fact, the proof shows something stronger. If you want a pole of order n, then you need at least n components in the resolution for which minus nu over n is equal to the real part of S0. And these components must intersect in a point. This is just a consequence of the local calculation on a resolution in local coordinates. The only way you can see a pole of order n appear is if such a situation exists in your resolution of singularities. Now we translate this picture into well, our weight function on our dual intersection complex. So these n components intersecting in a point, they give rise to a phase of dimension n minus 1 in the dual intersection complex. And such a phase is automatically maximal because this is the largest possible dimension that a phase can have. And so the vertices of this phase correspond to the n components. And so this means that each of these vertices, the weight function is equal to minus the real part of S0, because it's given by nu over n. And so since the weight function is affine on the phase, if it takes the same value on all the vertices, then it must be constant. So we have found a maximal phase of constant weight, and the weight is equal to minus the real part of the pole, S0. But then we're done, because then the theorem tells us that this can only happen if the real part of S0 is minus the log canonical threshold. And that's exactly the result that we wanted to prove. So in fact, I should say both in the statement of the conjecture and in the proof and in the statement of the theorem here, sweeping something under the rug. So the conjecture and the theorem here are only true locally around points of the zero locus of F. This doesn't have any influence on the argument that I'm giving, and it avoids a couple of technicalities to phrase it like this. So there is a small caveat to get a completely correct statement. I will explain what needs to be done when we discuss the technical aspects of the proof using minimal model program. Then, well, we also tried to collect some further evidence for this slogan. And so one thing one can prove, for instance, there are other theorems of a similar flavor, is the following. So denote by sigma min the locus of minimal weight. So this is the set of points in the dual intersection complex sigma where the weight function takes value minus log canonical threshold, or a better log canonical threshold, sorry. And so assume that the polynomial f has no multiple factors, so that the zero locus of f is reduced. And assume that the singularities of f are not too bad, meaning that the log canonical threshold of f is equal to 1. So in this case, we call the singularity log canonical. Then one can show that there exists a collapse of the whole dual intersection complex sigma onto the locus of minimal weight. And so collapse is a particular type of strong deformation retraction that one can define for simplicial complexes. And this collapse is compatible with the weight function in the following sense. So if we fix any value w, which is at least a log canonical threshold, then we can look at the subcomplex of sigma, which is spanned by all the vertices where the weight is bounded by w. And our collapse of sigma into sigma min simultaneously collapses also all of these subcomplexes onto the locus of minimal weight. So this implies in particular that all of these complexes are homotopy equivalent to each other. And this is also consistent with the idea that there should be a gradient flow induced by the weight function contracting or collapsing the whole space sigma onto the locus of minimal weight. So there's a similar theorem in the case where F does not define log canonical singularities, but well, I don't think it's very meaningful to formulate it here. So let me keep it at this.
Can I ask a quick question? So a collapse is essentially a composition of elementary collapses, which yeah, the maps of simplicial complexes defined in a certain way, that you are removing the interior of some simplex opposite some face.
That's right.
Yeah, so when you say that this collapse simultaneously collapses, does it mean that it preserves this kind of sequence of elementary collapses? So you have like the sequence of elementary collapses for the whole complex, and then for each W, you have a subcomplex.
Yeah.
And you say that then you can just kind of get a tail of this composition of elementary collapses, and that will will preserve this subcomplex and will turn out to be a collapse for it.
That's exactly right.
Okay.
Yeah, so if you restrict your collapse to the faces that are contained in one of these subcomplexes, then well, either you get the identity if you're not collapsing anything in here at all, or it will be an actual elementary collapse inside the subcomplex.
Okay, thanks.
And what's the point of having LCT equal to 1? Why do you need that?
So the theorem is false if the LCT is not equal to 1. So if the singularities are worse, if you're not in the log canonical case, then the statement is true only if you build your dual intersection complex using only the exceptional components in the resolution. So you need to ignore the vertices that would correspond to components of the strict transform of the zero locus of F. Okay. Is that an answer to your question?
Yes, yes, sorry, I was muted myself.
Okay.
So in this case of the cusp, it's miraculously true, even though it shouldn't.
That's right. That's right.
Okay.
That's right. But yeah, in the paper we produce counterexamples to this statement in a non-log canonical case. Oh yeah, sorry. I actually wrote it down. So if the log canonical threshold is not 1, then if it's strictly smaller, we need to restrict to exceptional components.
Sorry, can I ask something else?
Sure.
So there are more kinds of, well, depending on the situation, you can put other sorts of decorations on the vertices as well, right? So for example, you can remember whether or not it is exceptional or not.
Right.
Like, does it make sense to expect that a general statement exists if you take into account additional decorations, or do you not have something like that in mind at the moment?
I should think about it. I should think what is actually compatible with the counterexamples that we gave. But yeah, it's a fair question. If you take into account the fraction, well, both the weight and whether it's exceptional or not, so maybe you can get some kind of more uniform statement that covers the two cases. That's a good point. I'll think about it.
Okay.
Other questions at this point? So if not, let me say a little bit about the motivation for the slogan. So, well, why we believe that such a thing should be true, even if we can't turn it into a precise mathematical conjecture. And so the motivation comes from mirror symmetry. Well, I'm going to tell you a couple of things that already showed up, for instance, in the talks by Alberto and Karim. But very quickly, in string theory, the universe is represented by usual spacetime, R3+1, and then an additional 6 real dimensions, taking the shape of complex Calabi-Yau threefold. And the theory actually predicts that Calabi-Yau threefolds and more generally Calabi-Yau manifolds come in mirror pairs, which have interesting symmetries between them. There the mantra is that the complex geometry of a Calabi-Yau threefold should be equivalent, whatever that means, to the symplectic geometry of the mirror partner. And so this has far-reaching implications in algebraic geometry. For instance, Candelas and his co-authors, they used this idea to predict numbers of rational curves on the quintic threefold. So that was a long-standing problem in algebraic geometry. This is the calculation of so-called Gromov-Witten invariants. And Candelas and his co-authors managed to pull this off by using mirror symmetry to reduce the calculation to a calculation of period integrals on the mirror partner, which is easier to do. But so the big challenge is, well, if you're not a physicist, but you approach this phenomenon from a purely geometric viewpoint, what's the geometric meaning of being a mirror pair? So what's the precise definition, and how can we construct mirror partners? So an influential conjecture that attempts to give a geometric explanation for mirror symmetry is the Strominger-Yau-Zaslow conjecture. So it states that members of a maximally degenerating family of complex Calabi-Yau varieties of dimension n admit a fibration into special Lagrangian tori of over a base of real dimension n. In fact, we expect the base to be a topological n sphere. So this conjecture was also mentioned by Dimitri a couple of months ago, back when we were still allowed to have seminars at the department, when he talked about Gromov-Hausdorff convergence. Now, it's extremely difficult to produce such Strominger-Yau-Zaslow fibrations, such SYZ fibrations, if you stick to differential geometry. But a beautiful idea of Kontsevich and Zeubelmann was that such a fibration can be found in the world of non-archimedean geometry, the world of Berkovich spaces. So Berkovich spaces have appeared already in the previous talks in this seminar. But for our purposes today, the most convenient way to think about them is as spaces which are made up from infinite collections of dual intersection complexes. In fact, if X is a smooth and proper scheme over the complex Laurent series field, then we can take the analytification of X as a Berkovich space over this field endowed with the t-adic absolute value. And a very convenient way to describe the topology on this Berkovich analytification is by taking a projective limit over all strict normal crossings models of X, of sigma of X, where sigma of curly X is the dual intersection complex of the special fiber of this normal crossings model. And so by definition, the special fiber X0 obtained from our model by putting t equal to 0 is a strict normal crossings divisor. So we can define a dual intersection complex as before. Then if one model dominates another, then we also get a map between the associated dual intersection complexes. And by passing to the projective limits, what we get is precisely the topological space underlying the Berkovich analytification. So from this point of view, dual intersection complexes appear naturally if you study the geometry of Berkovich spaces. And so why is it reasonable to think about non-Archimedean geometry in the context of the SYZ conjecture? Well, geometrically, we can think of our scheme X as a family of complex projective manifolds over a very small open disk. So a complex disk with the coordinate t and defined by absolute value of t smaller than eta, where eta is very, very small. But again, this is not a precise statement, it's just a geometric picture to keep in mind. And then the Berkovich identification of X can be thought of as some kind of limit of the fibers as t goes to 0. So we don't actually reach the special fiber of any model. We don't put t equal to 0, but we bring t infinitesimally close to 0, and then the reasonable object that occurs is this Berkovich identification. So it's kind of limit object for degenerating families. And so this is precisely the place where we expect the SYZ conjecture to apply. Now, if X is Calabi-Yau, or more generally, when the canonical bundle of X is trivial, then one can define on this Berkovich identification of X a weight function, which is well defined up to an additive constant. And the base of non-Archimedean SYZ fibration, so this non-Archimedean picture that was proposed by Kontsevich and Zeubelman, that's precisely the locus where the weight function is minimal. So what is the heuristic that we borrow from mirror symmetry? So in the degeneration, the idea is that the fibers of the SYZ fibration are collapsed in the sense of Gromov-Hausdorff convergence, as was explained by Dimitri. So we can think of this as inducing a flow in the direction of decreasing weight, because we arrive in the skeleton, the locus where the weight function is minimal. So if you believe somehow this non-Archimedean version of mirror symmetry that was proposed by Kontsevich and Zeubelman, then you expect that something like this should hold. And again, if you want to turn this heuristic into a precise statement, you need to work harder. You need to do some more serious non-Archimedean geometry and use some very serious minimal model program techniques. But that's not something I want to discuss today. So I just hope that this explains more or less why it's natural to come up with this slogan in the first place. But to give you an explicit example, we can look at the case of state elliptic curves, which is somehow the simplest non-trivial example where the non-Archimedean SYZ conjecture or where the non-Archimedean SYZ fibration should appear. So a theta elliptic curve, this is just an elliptic curve over the complex Laurent series field, which has semi-stable reduction and such that the special fiber of its semi-stable model is a cycle of P1s. And so I've drawn one example here in blue. So I started from a well-chosen elliptic curve over the complex Laurent series field. I've taken its minimal strict normal crossings model, and I assume that the special fiber of this strict normal crossings model is a cycle of 3 P1s, which intersect as indicated on the picture. And so then we can form the dual intersection complex, which in this case has 3 vertices corresponding to the 3 reducible components. And then these 3 vertices are connected by 3 edges corresponding to the 3 intersection points. So topologically, the dual intersection complex is a circle. So to build the Berkovich space, we need to take a projective limit over all strict normal crossings models. And so essentially, this means that we need to modify our minimal strict normal crossings model by blowing up points. And we can perform 2 types of blowups. So the first type is blowing up a point which is an intersection point of components in a special fiber. So that's pictured here. So this means that we separate 2 of these blue components by means of a new green component, the exceptional divisor of the blowup. Then if we look at the impact on the dual intersection complex, we see that the topology of the dual intersection complex doesn't change. The only thing we've done is adding an additional vertex, which is the green vertex here, which lies in the middle of the 2 red vertices corresponding to the components containing our green point. So the first type of blowup induces a subdivision of the dual intersection complex. We add a vertex, but we don't change the topology. Then there's a second type of blow up that we can carry out. So we can blow up a point which is not an intersection point of two components. And in this case, something different happens. So we add an exceptional component, which is the yellow component here in the picture. And so now we do change the topology of the dual intersection complex, because we get this new vertex here, and we also get this new edge corresponding to the intersection point of the yellow component, which is blue component. Yeah, so the second type of blow-up has the effect that we add a small line segment to one of the vertices from our previous step. So now we take a projective limit over all such point blow-ups. And if you pass to the projective limits, the picture that appears is this one. So that's analytification of the theta elliptic curve. So in the center, you see the circle that we started from. And in fact, this is exactly the locus where the weight function is minimal in this case, locus of minimal weight. And then from this circle, you will have infinitely many trees that branch at infinitely many points in infinitely many directions. So you get a very widely ramified kind of collection of trees that are all glued onto this circle. And so the way the weight function behaves on this picture is that, again, it's constant in the middle, there it's minimal. And then it's strictly increasing when you start moving away from the circle on one of these trees. If you put the natural metric on this Berkovich analytification, which I won't discuss in detail here, but then your weight function will actually just have slope 1 as you move away from the circle in the middle inside the Berkovich space. And again, in this case, we indeed see that the weight function gives you a deformation retract onto the circle in the middle if we start from any point and we move in the direction of decreasing weight. So also in this one-dimensional situation, you can actually make the heuristic precise. So the last thing I wanted to do was to explain the proof of the main theorem using MMP. I don't know what you prefer. If you prefer to have a break now, I think I have about 20 or 25 minutes left to talk.
Doesn't matter to me. Both ways are okay.
I vote let's go on.
Okay, let's go on. So this part of the talk will be more technical than the first part, because we will actually start using some serious MMP stuff. But I'll try to explain the intuition between the steps as best as I can. So we're going to prove a result which is a little bit more general than the main theorem that I formulated before. So we take a field K of characteristic 0. We take any smooth connected K variety X with a dominant morphism to the affine line. And we take a point X in the zero locus of F. And so in our previous setting, F was a polynomial in n variables, and then X was just affine n states. But the theorem holds in this greater generality.
X is compact.
No, not necessarily. No.
Sorry, the morphism is proper.
No, also not.
No assumption on this, okay.
And so we take a log resolution for F, H. So this is the type of resolution of singularities that we've considered before. So this means that H is proper and birational, Y is smooth. We assume that H is an isomorphism away from the zero locus of F. And we assume that the inverse image of the zero locus of F is a strict normal crossings divisor on Y. By embedded resolution of singularities, such a morphism H always exists. And just like before, we can attach numerical data to this resolution in the following way. So we take the pullback of the divisor of F through the resolution H, which we write as a sum over I in some index set capital I of, well, we get irreducible components EI, and each of them comes with a multiplicity NI. So this is the order of vanishing of F along the component EI. And then we have the relative canonical divisor, which we use to define the log discrepancies. So the log discrepancies nu I are defined by the property that nu I minus 1 is the coefficient of EI in the relative canonical divisor. So this somehow measures how deep the component EI is located inside the resolution of singularities. And now, well, this is what I swept under the rug before. In fact, Wim's conjecture is really a local statement about the local log canonical threshold points and the local p-adic zeta function at a point. This means that we will need to localize the setting of our theorem as well. And so the assumption that we're going to make is the following. So for every subset J of the index set capital I, we can consider EJ. This is the intersection of all the components which are indexed by capital J. And so I'm going to assume that as soon as EJ is non-empty, then it must intersect the fiber of the morphism H over X. So this we can always do by shrinking the variety X around the point little x, because H is proper and each of these EJs is closed. So when EJ does not intersect H minus 1 of X, then the image of EJ under H will be a closed subset of X, which does not contain the point little x. And so we can just remove this closed subset from X to reduce to this situation. So this is a condition that we build in, reflecting the fact that we're really proving a local statement on X. Then we define a dual intersection complex sigma of our divisor of F composed with H as before. And we can also define a weight function in exactly the same way as before. So this is a real valued function on the dual intersection complex, which is affine on all faces and such that the weights at a vertex Vi is equal to nu I divided by Ni. So the vertices of this complex correspond to the irreducible components Ei. So Vi is the notation for the vertex corresponding to the component Ei. And then this component has numerical data, Ni and Ui, which we use to define the weight function at the vertex. And so now the precise formulation of the theorem is that if the weight function is constant on a maximal phase of sigma, then the value on this phase is the log canonical threshold of F, which is still equal to the minimum of the fractions nu I over Ni, where I runs over the entire index set capital I. So to prove this theorem, we're going to translate it into a statement that no longer involves weight functions or dual intersection complexes. So what are we really saying by stating this theorem? We're saying that there exists a subset J of I and a connected component C of EJ such that the following is true. So this connected component C will correspond to a phase in a dual intersection complex by definition. And so we want that this phase is maximal, that it's not included in any strictly bigger phase. But that's the same thing as saying that this component C does not intersect any other irreducible component EI. It's saying that we have a bigger phase spanned by the phase of C and some other vertex VI. That's the same thing as saying that the component C intersects EI. And so this is what we want to exclude. So that's maximality of the phase. Then we express the property that the weight function is constant on the phase corresponding to C. So that means that the value of the weight function at the vertices, which correspond exactly to components EJ with J in capital J, that this value is constant, that it's independent of little j. And so we give this value a name, we call it W. So W is the constant value of the weight function on the phase corresponding to C. And then what we need to prove is that if this happens, W must be equal to the log canonical threshold of F. So the idea behind the proof is to run a minimal model program on, well, Y, which is the variety appearing in our resolution, and dy, which is a Q divisor on Y that we will need to construct in a careful way. So we write a divisor of F as A plus B, where A and B are effective divisors without common components, such that, well, we divide the components of divisor of F into two types. So the ones that go in A are the ones for which W A is bounded by a ret. So a ret is just divisor A where we put all the coefficients equal to 1. So this means that in this part A of the divisor of F, we collect components for which W is what is it? Is at most equal to 1 over the multiplicity of the components. So that's a condition that appears here.
And what's W? This is the constant value of weight.
W is our constant value of weight, that's right. And then we have the remaining part of the divisor, which is characterized by the property that WB is strictly larger than B red. Or, well, if such components don't exist, then B is equal to 0. And in fact, our conclusion in the end will be that W is the log canonical threshold of F. And this implies that B must be equal to 0. Because it implies that W is certainly smaller than or equal to 1 over n for all multiplicities n appearing in the divisor of F. So all the components go into this part. But that's something we can't say from the start because we don't know yet that W is actually the log canonical threshold. So in the course of the proof, one of the things that we are going to show is that B must be equal to 0. But since we don't know this from the start, we need to define A and B in this way to make the argument run.
Johannes, a question. When you write divisor of F, you're working on the resolution space.
No, this is on X.
This is really on X itself. Okay.
That's right. So I don't consider any exceptional components here. This is really on X.
Okay.
Yeah, thanks. That's a good question. So now we define a divisor D on X, which is, well, we multiply the A part of our divisor of F by W, and we add B red. So again, this is just a divisor B where we put all the coefficients equal to 1. So by definition of A and B, this is the same thing as taking the minimum of W times the divisor of F and the reduced divisor of F, where the minimum is defined component-wise. So for each component in divisor of F, we check what is smallest, either 1 or W times the multiplicity. And the smallest one we take as a coefficient of that component inside the X. So this gives us a divisor on X. And now we produce a divisor on the resolution space Y by taking, okay, this strange notation is just a strict transform of dx. So we take the strict transform of dx in the resolution as a first term. And then we add the exceptional locus with multiplicity 1 in each component. So this part is somehow horizontal. So these are strict transforms of components on X. And this part is vertical. All of these components are contracted by the morphism H. So one remark we can make right away is that the components Ej, which show up in our maximal phase of constant weight, so for J in capital J, each of these components appears with multiplicity exactly equal to 1 in the divisor dy. Now, if it's an exceptional component, then it's just by definition, because all of the exceptional components occur with multiplicity 1. And if it's not an exceptional component, if it lies in the strict transform, well, then the log discrepancy is equal to 1. So this means that nu j divided by nj is equal to 1 over nj. That's equal to w. That's exactly the definition of w. So if we multiply our divisor with w, we set the coefficient of this component equal to 1. And so that's a component with which it will appear in this divisor. And so this is important to remember. All the components that we care about, especially all these EJs, they appear with multiplicity 1 in the divisor dy. And so now we run a relative minimal model program with scaling on the pair consisting of the variety y and the divisor dy, relative over x. So every step of the MMP will actually be a birational map of schemes over x. So if you don't know exactly what this means, well, I hope that the argument I'm going to give will still make sense to you nevertheless. The point of running this MMP is that we transform the pair y dy into a new pair z dz, which still lives over the scheme x. So it's almost a strict normal crossings pair. So it's not exactly true that z is smooth, and it's not exactly true that dz is a strict normal crossings divisor, but we're still pretty close to that situation. And this is expressed in a technical way by saying that this pair is DLT. So DLT is just a class of singularities of pairs, which is defined precisely because these are the pairs that show up if you run an MMP on a strict normal crossings pair, as we did. If you haven't seen definition of DLT before, you can just pretend that this is really a strict normal crossings pair, so that Z is smooth and dz is a strict normal crossings divisor, and you won't lose much in the remainder of the argument.
What scaling means here?
Oh, this is just in order to have termination of the MMP. So this is a trick that was introduced, for instance, in the BCHM paper, where they prove that MMP terminates under suitable conditions. So you need to fix an ample divisor on Y, and you somehow use this divisor to steer the MMP algorithm. Yeah, it's just a technical point that guarantees that the MMP will run in finite time. Is that okay?
Yeah, okay. I don't know. Maybe you could say. I don't know, I'm not trying to force you to explain the MMP in 5 minutes, but maybe you could say what in concrete terms this produces, that we start with a pair, and what we get is a sequence of birational transformations of y.
I will tell you in a bit precise steps of the MMP, because that will be important in the proof. So right now, the only thing we need to know is that what rolls out is the DLT pair Z dz, which we can think of as being a strict normal crossings pair for practical purposes. And so dz is, you have a birational map from y to z, and dz is just a push forward of dy to z. And so some of the components in dy will be contracted, some of the components will survive, and these will be the components in dz. But yeah, I'll explain the individual steps of the MMP in a bit. But the scaling is just a way to select the extremal rays that you want to contract in the steps of the MMP. And whoops, sorry, I should finish. So of course we had a nice strict normal crossings pair to begin with. So what it is the advantage of passing to this new pair Z dz. Well, the point is that it's minimal in the sense that kz plus dz is numerically effective over X. So the BCHM paper guarantees that such an MMP can be carried out, and that this will indeed be the end product. So the key point of the proof is the fact that running this MMP, so passing from Y to Z by means of a birational map, does not affect this connected component C of the intersection of the components E little j. So this birational map will actually be an open embedding around C, meaning that none of the components EJ occurring as vertices on our maximal phase of constant weight, none of these components is contracted by the MMP. And well, since they all appeared with multiplicity 1 in dy, they still appear with the same multiplicity 1 in dz, because dz is just the push forward of dy under this birational map. So in order to explain these key points, I will need to answer Dimitri's question and say something more about the exact steps of the MMP. So I'm going to postpone that for a little bit and first continue to deduce our theorem from this key point. So since we have run an MMP over X, the end product Z is still a scheme over X. And then we define a new divisor, dz prime on Z, in the following way. So we take the relative canonical divisor of Z over X. We add the divisor dz, which appeared in the end product of our MMP. And then we subtract the pullback to Z of W times the divisor of F. And so now we can study the coefficients of the components that appear in this sum. So we will have a bunch of exceptional components, which we package in this first term, the exceptional. And then we have a bunch of components which are in the strict transform of the divisor of F. But since we've subtracted W times the divisor of F, and since all the components that come from A occur with multiplicity W times the multiplicity in dz, these will all cancel out by taking this difference. And so for the components that belong to A, the way they appear in dz is exactly as plus the pullback of W times the way they appear in divisor of F. So the components from A all cancel out in this difference. And what we're left with are the components in the strict transform of B. Because these occur with a factor W in this negative term. And by construction, they occur with a factor +1, with a coefficient +1 in dz. So that's our non-exceptional part of the divisor, minus the strict transform of WB minus B red.
So sorry, so the MMP is relative to not to phi but to F, or is it relative to phi?
Again?
The MMP that you run is relative to which morphism, phi or F?
Well, phi is the result from the MMP. So we start from the resolution morphism H, which gives Y structure over X. And then we run the MMP so that this X structure is preserved. And so we end with a variety which still lives over X. And so this structural morphism we call phi. So this divisor, dz prime, is still nef over X because, well, we know that kz plus dz was nef. That's the effect of the MMP. And then the only thing we've done is we've added or subtracted pullbacks of divisors on X. But that doesn't change the property that doesn't change nefness relative to X. That's a consequence of the projection formula. So if we have something relatively nef over X, then we can add or subtract pullbacks of any divisor living on X, and the nefness will still be preserved. And moreover, again, by definition of the B divisor, WB minus B ret will be effective, because the components in B are exactly those for which W times the coefficient is strictly bigger than 1. So now we can apply one of the key technical lemmas in the MMP, which is called the negativity lemma. And this negativity lemma implies that then minus dz prime must be effective, and that its support must be a union of fibers of phi, of the morphism from Z to X. And so we know that it's a divisor. So either it must be a divisor containing phi minus 1 of X, or it must be empty. Why? Well, the only possible components that can appear in this divisor are the components in the pullback of the divisor of F, because we simply don't have any other divisors in the picture that we can choose from. but by our local assumption that I made in the setup of the theorem, all of these components will intersect phi minus 1 of x. Otherwise, we would have removed them from the resolution. So either it must contain phi minus 1 of x, or it's empty because, well, again, all the possible components that we can use inside minus dz prime are ones that meet this fiber.
Could we dwell on this a little bit more? What is the statement of negativity lemma?
It says exactly this. So we have this this morphism. We have this divisor which is NF consisting of exceptional parts and minus the strict transform of something effective. Then if this thing is NF, then it must be anti-effective. So minus the divisor must be effective, and the support must be a union of fibers.
Okay, thanks.
Yeah, so this is literally the statement of the negativity lemma for this morphism phi and for this divisor. But well, no component EJ with J in capital J can appear in dz prime because well, if
sorry, I'm stupid. I didn't get the last consequence before. Like, okay, then you apply the negativity lemma, and
yeah.
How do you deduce that it is a divisor containing the preimage of x or empty?
So all possibly reducible components that can appear in dz prime are components of the total transform of divisor of f. The complement of this divisor phi is an isomorphism.
Okay.
But we've set up the picture in such a way, we've shrunk x around the point little x in such a way that all the components that appear in the resolution intersect phi minus 1 of x. So yeah, this means that either our divisor minus dz prime intersects, contains phi minus 1 of x, or it's empty because it can't contain any components at all.
Okay, okay.
Now, none of the components EJ with J in capital J can appear in dz prime because, well, by the definition of W, if you calculate the multiplicity of this component in dz prime, you will find 0. You will get a cancellation between the log discrepancy, which appears in these terms, and W times the multiplicity in of the divisor, which appears in this term. And so by definition of W, all of these components are killed in the definition of dz prime. And C doesn't intersect any other component of dz prime. This is the assumption that C actually doesn't intersect any other irreducible component EI at all. But it still meets phi minus 1 of x, because every stratum in the resolution meets phi minus 1 of x. That's again the locality assumption that we have built in. So this means that dz prime must actually be equal to 0. Because if it's non-zero, then it must contain phi minus 1 of x. So that means that it must intersect C. But then it would need to contain one of these components EJ, because there are no other components intersecting C, and that's a contradiction. Now, saying that dz prime is equal to 0, well, that means in particular that WB must be equal to B red. But by definition of B, that's only possible if B is actually equal to 0. This divisor is effective. So the only way that these two can be equal to each other by definition of the component B is when B is actually equal to 0. All right, so then using the fact that B is equal to 0, we can actually rewrite the expression for the transform dz, so the divisor on the minimal model Z. So dz will then be equal to minus the relative canonical divisor of Z over X plus the pullback of W times the divisor of F. So this is just this formula again, but now using the fact that we've proven that dz prime is equal to 0. So we use this to write dz as minus the relative canonical divisor of z over x plus the pullback of W times divisor of F. Now, since the pair z, dz is DLT, and we know that dz contains components of multiplicity 1, for instance, the components Ej. Well, that implies that the log canonical threshold of this pair is actually equal to 1. The DLT condition guarantees that the pair is log canonical, so that means that the log canonical threshold cannot be strictly smaller than 1. But the components Ej appear with multiplicity 1. So this gives us that the log canonical threshold is at most equal to 1. And so we must have equality. Log canonical threshold of this pair must be equal to 1. And so this is a partial resolution for the pair x dx that we can use to compute the log canonical threshold of F. And so since, well, inside dz, we had not exactly divisor of F that appeared, but W times divisor of F. This has the effect of multiplying the log canonical threshold with a factor W. So log canonical threshold of F is equal to W times log canonical threshold of the pair Z dz. And then, as I've just explained, this log canonical threshold is equal to 1. So we find that log canonical threshold of F is indeed equal to W, and that's what we wanted to prove.
Sorry, do you have any idea what the support of dz can be? Or is it something you can't say explicitly?
Let's see. So it should be, again, I should think about this carefully to be sure, but it should be something like the components in a strict transform of divisor of F plus the exceptional components computing the log canonical threshold. So for which nu over n is equal to the LCT.
Okay, so kind of the dual intersection complex of dz is the part of dual intersection complex that on which the minimum is reached?
That's right, except that we also still need to include the exceptional components. Sorry, that we still need to include the components of the strict transform. Those are always there simply because we've run a relative MMP over X. So we still have this morphism from Z to X, and the components that exist in X will continue to exist in Z. But the exceptional components are those computing the log canonical threshold. That's right.
And so a priori Z is not smooth. It's just.
That's right. So the pair Z dz is DLT, which is an approximation somehow of an SNC pair, but it's not exactly the same thing. So Z will have singularities in general.
And sorry, could you repeat again how do you know that log canonical threshold of dz is 1?
Oh, so by definition of DLT, so this one part of the definition says that this pair is log canonical. Mm-hmm. And log canonical means that the log canonical threshold of this pair must be at least 1. Mm-hmm. Well, we also get an upper bound for the log canonical threshold because well, the log canonical threshold is computed by taking a log resolution and then computing the fractions nu over n and taking the minimum. So if we take this resolution in particular, we will find the strict transform of dz. And in this strict transform, we have the components Ej, which have multiplicity 1 and which have log discrepancy 1, because they are not exceptional in the resolution. They come from the strict transform of dz. Mm-hmm. So each of these will contribute nu over n equal to 1. So this means that the logarithmical threshold is at most equal to 1. And so we have two inequalities in opposite directions, and we get that logarithmical threshold is equal to 1. Mm-hmm. Is that an answer?
Yeah.
So what I still need to, well, that's well, a typo, obviously. So I still need to justify the claim that our MMP, our birational map from Y to Z, was indeed an open embedding locally around the component C. And so here we will need a more careful description of the individual steps of the MMP. So what does the MMP do? We start from our log resolution Y dy, and then we have a finite number of steps, each of which are birational maps. So we call Y dy Y0 D0. Then in the next step, this is transformed to a pair Y1 D1, and so on until at the end of the process, we obtain a pair YM DM, which is the end product of the MMP. So each of these steps is either a divisorial contraction or a flip. So it's a kind of birational surgery that we perform on the pair. And by the way the MMP is set up, both in the case of a divisorial contraction and a flip, this step will be induced by an extremal ray of the closure of the cone of curves over X. And this ray will be negative with respect to the canonical divisor of YL plus the divisor DL appearing in the pair. And so somehow these negative rays, they form the obstruction to nephness of this divisor. If this thing was neph, then it would have non-negative intersection with any curve. So we would have no negative rays at all in the cone of curves. So as long as we find negative rays, then we know that we haven't reached the end point of the MMP. We still have some negativity that we want to get rid of. And so we try to improve the situation by making this bad curve disappear, either by making a divisorial contraction or by making a flip. And so by induction on L, it's enough to show that our extremal ray R does not contain a curve intersecting C. So we're not flipping a curve intersecting C, and we're not contracting a divisor intersecting C. So assume the contrary, and then the important result that we use is a result by Florin Ambro. So it's a result about unicity of minimal log-canonical centers, which I won't explain here. But the implication for us is that the only components of multiplicity 1 in the divisor DL, which can have non-zero intersection with R, with our ray, are the components EJ with little j and capital J. And so the other components, well, either they have multiplicity strictly smaller than 1 in DL, or they have zero intersection with R. And what this means especially, and this is the form that we will use to finish the argument, is that R times E is equal to 0 for every other component contracted on X. So if we have an exceptional component which is different from the EJs, then R times E must be equal to 0. Because by definition of the divisor DL, exceptional components appear in DL with multiplicity 1. And so by Ambro's result, the only such components that can have non-zero intersection with R are the EJs. And it also means that every component in a strict transform of B has zero intersection with R, because these also appear with multiplicity 1 in the divisor DL by the definition of the divisor dy that we started the MMP from. Now, of course, I mean, a few slides ago, we have proved that B is equal to 0, but for that, we've actually used the claim that I'm now proving. So we're back in a situation where we don't yet know that, that B is 0, and we still need to take B into account. And now we compute. Again, we're running an MMP over X, so we still have a morphism from YL to X. And we compute the intersection multiplicity of R with KYL plus DL. And so we're assuming that R was a negative extremal ray inducing one of the steps of the MMP. So this intersection product is negative. But now we're going to show that it's actually 0, and that's the contradiction that will finish the proof. So we're computing relative intersection products over X. R is a relative curve class over X. So this means that the intersection product doesn't change if I change the second factor by adding pullbacks of divisors from X. And so in this way, I can change KYL into the relative canonical divisor by subtracting minus the pullback of the canonical divisor of X. And I can also subtract minus the pullback of W times divisor of F. So the intersection product doesn't change. Now I just use the definition of DL. So the definition of DL is that it's the reduced exceptional locus. So that's the reduced relative canonical divisor of YL over X, plus the strict transform of WA. Plus the strict transform of B, but we've already observed that components in the strict transform of B have 0 intersection with R. That was the consequence that we drew from Ambros' result. So we can just ignore the components from B in this calculation. And then for all components that appear in the resolution, we can compute their multiplicity in this expression. So the first 2 terms, well, each component EI will appear here with multiplicity equal to nu I minus 1 in this term and 1 in this term. So we get, for the exceptional components, we get multiplicity nu I. And then in the pullback of this divisor, we get W times Ni, the multiplicity. Again, we can ignore all the components that live in the strict transform of B. But in this entire product, we can also ignore all the exceptional components different from the EJ, because they will pair to 0 with R, once more by Ambros' result. And then we have one more term, which gives us plus the strict transform of W times A. So this will kill off all the components in the strict transform of A, because they will appear with the same multiplicity in this term and in this term. And so maybe I should do that again, because I don't think I've made myself very clear. So we'll look at this expression. And well, we know that the only guys that can have non-zero intersection with R are the components EJ and the components in the strict transform of A. And the other exceptional components give 0 intersection, and the components in the strict transform of B, they also give 0 intersection. So now for each of these components, we try to compute how they appear. Now, if we have components appearing in the strict transform of A, in this expression, they get W times their multiplicity. And in this expression, they get minus W times their multiplicity. So components in the strict transform of A are killed in this difference. So the only thing left to consider are the exceptional components that are among the components EJ. And then what is the multiplicity of each of those in this expression? So here they get multiplicity nu j minus 1. Here they get multiplicity 1, so that adds up to nu j. Here they don't appear at all, because this is a strict transform of a divisor on A, and so it doesn't contain any exceptional components. And here they appear with multiplicity W times Nj. So that's the second part of the coefficient here. So in the end, the right-hand side is equal to the sum over all the exceptional EJ of nu j minus W and J times EJ. But by definition, W is equal to nu j over Nj for all these components EJ. And so we find 0. And this contradicts, well, the choice of R. R was supposed to be a negative ray, so it should have negative intersection product with this divisor. But we compute that it's equal to 0, the intersection product. So this is a contradiction, meaning that indeed every step of the MMP is a local embedding locally around, an open embedding locally around.
Can I quickly ask a naive question? So the way MMP is defined, DLs, it's important to define just birational transformations, and DLs we can compute by this formula, like relative canonical bundle reduced plus strict transform of dy.
That's right. So, well, there are two ways in which you can define the DL. So either you take the birational map from Y to YL and you take the push forward of dy. But that's actually the same thing as taking the reduced exceptional locus of the morphism psi plus the strict transform of the divisor of F. Plus the strict transform of dx. That's right.
Wait, who is dx in the setup? Is it the divisor of the first pair that we started from?
That's right. Dx was the divisor WA plus B.
Ah, okay. I thought it was called dy.
No, right. So dx is a divisor we construct on X before any resolution. So that's A plus B reduced. So that's the same thing as the minimum of W times divisor of F and the reduced divisor of F. And then dy is the logarithmic transform of this divisor on Y. So which means the strict transform plus the reduced exceptional locus. Now, if we start pushing this divisor to one of the steps in the MMP, one of the YL, the reduced exceptional locus remains the reduced exceptional locus, and push forward of the strict transform, that remains the strict transform. So this is actually valid on each of the YL as well.
Mm-hmm. Okay, thanks.
Any other questions? Actually, this was my presentation, so I'll be happy to take questions if you have some.
Yeah, Johannes, a non-precise question. So you had this slogan, and the idea is to turn this slogan gradually into a more concrete theorem. Mm-hmm. Did you do something about that, let's say, last half year or not, or something that I don't know?
The one thing I've been thinking about a little bit is, well, in the simplest situation where you have strict normal crossing pairs, you have this retraction map of Berkovich to the skeleton. And I think one can reconstruct that in a more canonical way using the weight function. But that's as far as I got right now.
Okay.
So what does your slogan say in the case of this thing homeomorphic to S2? How could the flows look like on a space like that?
In the picture of well, you have like a baby case in the picture of the elliptic curve.
No, but on the one that isn't the one that is the, if you go back a little bit further,
yeah,
to the three-dimensional example or the two-dimensional example.
Yeah.
This one, yeah. So, for example, if now the ground plane was constant, if the weight function was constant there, would that be possible?
Be constant everywhere.
Then it has to be constant everywhere, right? So it's not possible that it's higher than at the top only.
No, that's right.
Yeah. Okay. No,
so one way to see this is that the homotopy type of the level sets cannot change. If it's constant on the lower face, then it must be constant everywhere.
So are these kinds of implications from your slogan, are they known already? So this sort of statement?
Well, it's kind of a special case of the second piece of evidence that I presented. So you have well, here I formulated it in the case of hypersurface singularities. But we actually have completely analogous theorems when you start from a degeneration of Calabi-Yau and you consider the weight function there. And then we have a similar statement saying that if you have any strict normal crossings model, then there's a collapse of the dual complex onto the essential skeleton, so the locus of minimal weight, which respects all the level sets. And so in particular, all of these level sets must be homotopy equivalent to each other.
I see, okay.
But the proof is still MMP. So that's kind of the frustrating thing. You have this very geometric and, well, I hope conceptual picture that is suggested by non-Archimedean geometry. But at this point, we don't know how to prove such a statement using just non-Archimedean geometry without invoking the MMP.
Hmm.
Well, you would need to somehow have fibers of the retraction as a geometric object.
That's right. Yeah, so you can try to use the weight function to parameterize the time of your strong deformation retract. But the trouble is that it's not so clear what would be, well, for one thing, the strong deformation retract that you construct using the MMP depends on a choice. You run this MMP with scaling with respect to an ample divisor. And this ample divisor will steer the deformation retract as well. So this is something you would need to incorporate into the picture if you want a non-Archimedean proof of this result. So the weight plays some kind of role of time parameter that allows you to travel over paths, or well, better the difference between the weight and the minimal weight. But then you still need a way to select the actual path that you're going to follow. And somehow it's not determined just by the behavior of the weight function itself. So there is some additional piece of information that we're not quite seeing.
So why is it not determined just by the weight? Right, you have this function and it has a gradient, right?
That's right, but so there are situations where you don't really know how to choose the path that you're going to follow. You can imagine, for instance, a situation where you have maybe you have a triangle and the weight is minimal in one of the vertices. For each point of the triangle, you would like to have a canonical way to decide how to travel to this one vertex. And so you can actually find situations like that which do occur where the weight function doesn't give you an unambiguous strategy to reach the locus of minimal weight. Does that make sense?
Sort of, but don't you just, I mean, if you just imagine the triangle is lying in like R2 with versus the origin 1, 0, 0, 1,
mm-hmm.
and you have a function on that, you can just follow the literal naive gradient, right?
Mm-hmm.
Of the function. And this gives you, let's say, a vector field by taking the partials, partial x, partial y, you put them in a vector, you get a vector field, and you take the flow lines.
Yeah, you're right. So probably my example of the triangle was poorly chosen. So I agree on an individual simplex. It's actually when you start gluing different simplexes together, you can reach situations where it's not clear what direction to follow, where you can somehow choose different orders. And you need a device that gives you a systematic choice of orders so that you can glue all your local constructions into a global retraction.
Yeah. Okay. Okay. So it's kind of like yeah. Yeah, you need to construct a vector field, let's say.
Yeah, that's right. And so
like a metric,
there is a notion of Morse theory for simplicial complexes, which is due to Robin Forman, discrete Morse theory. but the weight function is not a Morse function in that sense. And so it appears that you need some kind of small perturbation of the weight function, which resolves the ambiguities in the flow, and probably which is related to the choice of an ample divisor to do the scaling for the MMP.
Mm-hmm. Okay.